Okay, so we're finally getting to the good stuff here. This section marks the beginning of several sections where we will work out some very useful tests for establishing whether a series is convergent or divergent. I like to compare this moment with when you were learning to take a derivative. The integral test is sort of like finding a derivative via the limit of a difference quotient. It works, but it's clunky and exhausting. The comparison tests of this section, along with the tests in the next couple of sections, are like learning the product rule, the quotient rule, and the chain rule. They're the good stuff. They're slick, they're useful, we're going to be using them all the time. So, yeah, just to kind of bring in this topic, let's recall that last time we showed this particular series was divergent via the integral test. All right, so in this section, we're going to show that this series is divergent using a comparison. And we're going to see that we can establish this result in just one or two lines of writing. So let's make a quick observation here. ln of n is greater than or equal to 1 eventually. Specifically, ln of e is equal to 1, and ln is an increasing function. So ln of everything greater than e, ln of 3, ln of 4, ln of 5, etc., those are all greater than or equal to 1. So dividing both sides by n, we get that ln of n over n is greater than or equal to 1 over n. We also know that this series is divergent. Right? It's the harmonic series. So the conclusion that we're going to draw is that since the terms of the series we're interested in are greater than or equal to the terms of this series here, which we know to be divergent, it must be true that this is a divergent series. So the main idea behind these comparison tests is that you've got a series that you're interested in working with, if you want to see if it's divergent or convergent. And you compare its terms with the terms of some other series that you already know something about. Okay? And if the comparison is in the right direction, then you can draw a conclusion about the series you're interested in. And what I mean by the comparison being in the right direction is if we're comparing to a divergent series, as we did in this example here, then the terms must be greater than or equal to the terms of the divergent series. On the other hand, if we were making a comparison with a convergent series, we need to show that the terms of our series are less than or equal to the terms of the convergent series, because the numbers need to get small quickly. So let's write down this test. This is called the direct comparison test. So let's suppose we have two series that we're interested in. AN is the actual series we want to know about, and we choose the series BN here to be some series we already know something about, like the harmonic series or NEP series, or a geometric series, which we could easily determine its convergence. So, okay. So if Bn is convergent and the terms of the series An are less than or equal to the terms of the series Bn, then we get to conclude that the series An is also convergent. All right, and on the other end of this, if Bn is divergent and the terms of An are greater than or equal to the terms of Bn, then the series An is also divergent. Okay, If you cannot establish the correct direction of comparison for the conclusion that you need, then we don't learn anything from that. Okay, so let's see some more examples of using the direct comparison test. All right, so let's investigate this particular series. So we'll see if this guy is convergent or divergent. Now, without the comparison tests, we would really have no choice but to use the integral test, right? It's not a geometric series, and the only other real test that we know is the divergence test, but the divergence test is inconclusive because this limit here evaluates to 0. So the divergence test is only conclusive when that limit is not 0, and that's really rare, right? We rarely encounter a series that looks like that because it just so obviously is divergent. So yeah, I don't want to do the integral test on this, so no problem. We're going to do the comparison test because that's where we are right now. So, okay. Now, one of the tricks to using the comparison test is that you need to come up with a good guess for what to compare to. You can't just compare to anything. So it needs to be possible to show the right direction of comparison, and you need to be able to pick a series that you expect this thing to share the behavior with. Moreover, the series that you pick to compare with has to be a series whose convergence or divergence you either already know or can easily establish to make the whole endeavor worthwhile. So when you've got a purely algebraic series like we have here, you can simply think about this as just the leading numerator term divided by the leading denominator term. Okay? And remember, the 5/2 here is just a constant that can even be thought of as pulled right out of the series in this hypothetical comparison series here. So we can expect that this particular series here is going to have the same behavior as the series 1/n². And in fact, for purely algebraic series like this one, this thought process is sound. This will work. So all we have to do is compare this with 1/n². We know the series 1/n² is convergent. It's a p-series. And the 2 is greater than 1. So we will use direct comparison. So to use direct comparison, there are 3 steps. The first step is writing out the comparison. So this guy here is clearly less than or equal to this guy here. Okay, and compare the terms, not the series. So we don't want sigmas in this step. All right, this is a true statement, and it's self-evident. So they have the same numerator, but the denominator of this term is greater than the denominator of this term, which means overall, this quantity is less than or equal to this quantity. Okay. Now, the second step is acknowledging or establishing the behavior of the series you're comparing with. So we're going to say here that this series is convergent. Why is that? It's a p-series. P is equal to 2, and 2 is greater than 1. All right, remember to justify everything. Well, we can immediately conclude that this guy here is convergent. In fact, let's put a therefore, because it's kind of our conclusion out of this. So the first 2 steps are assertions, and then we have our conclusion. And that's it. We're done. All right. Now be careful with your comparison step. That's obviously the trickiest part. For instance, you may have said, let's just compare to 1/n², and who cares about the 5/2? Well, this may be true, but it's not at all obvious, because 5 is not less than or equal to 1. So make sure that your comparisons are fairly self-evident. All right, so let's look at another example. All right, so what about this series here? Now this is not a purely algebraic series, so we can't just tie it directly with a p-series like you can with an algebraic series. But we actually can, because natural log is pretty predictable. So let's note something about natural log. We made a comparison earlier by claiming that eventually it's true that natural log of n is greater than or equal to 1. But it's also true that natural log of n is less than or equal to n. And that's actually true for all values of n. If you look at the graphs of y equals x, y equals ln of x, and y equals 1, that far enough to the right, and you don't have to go very far at all, y equals x is bigger than y equals ln of x, which is bigger than y equals 1, right? So it's true for n as well. And that means you can take advantage of this hierarchy when you have ln of n muddying up a series that you're working with, and you're just trying to establish whether that series is convergent or divergent. So we can see, since ln of n is less than or equal to n, then their reciprocals are going to exhibit the opposite relation. So 1 over ln of n is greater than or equal to 1 over n. Okay, well, great. Being a series whose terms are greater than the terms of a divergent series means that you're also going to be a divergent series. So we're basically done. We just have to finish writing out our proof. This is the comparison here. Okay. Let's also assert that this is a divergent series. Okay, and we can explain why just by writing out that it's harmonic, or you could even say it's a p-series. P is equal to 1, and what is it about the 1? Well, 1 is less than or equal to 1, which means that's a divergent series. And our conclusion is this guy is divergent. And there we are, handled. All right, well, what about this particular series? Okay, so there are going to be some limitations to the direct comparison test. And it may not be quite clear yet what those are, but this one's going to bring about one really big one here. So this is purely algebraic, which means we know that it ought to behave like a p-series. And in particular, it's not too difficult to see that the p-series this one's going to behave like is 1 over n squared. Which means that even before we start writing anything, we actually do know this is a convergent series, and all we have to do is prove it. The problem is that it's impossible to establish the direction of comparison that we would need when showing that a series is convergent via direct comparison, because this is not true. The denominator here is smaller than the denominator here, which means this whole fraction is actually greater than this whole fraction. So while there are other ways we could force a comparison like this to work by changing the right-hand side to say something like this, this is in fact eventually a true statement, and these are the terms of a convergent p-series because p is 3/2, which is greater than 1. In general, we need something a little cleaner, and we don't want to have to just stop and come up with a hack every time the direct comparison test isn't going to be giving us the direction of comparison that we need. So, fortunately, there is something that handles this situation very nicely, and that's called the limit comparison test. So, like the direct comparison test, we have two series, AN and BN. AN is the series that we're interested in investigating, and the series BN is a series we're comparing with that we already know stuff about. What we do is we evaluate the following limit. We're going to let C be the limit as n approaches infinity of the quotient AN divided by BN. So this limit is going to capture, or rather compare, the growth rates of the terms of these two series. If an and bn have approximately the same behavior, meaning they both grow quickly like they diverge, or they both shrink very quickly, meaning they converge, then this limit here is going to be a finite number, because basically that means that one of them doesn't pull away from the other. So when C is finite, then we would say that these two series have the same behavior. If C is positive and finite, so specifically if C is strictly greater than 0 and of course less than infinity, then these two series have the same behavior. In other words, they both converge or they both diverge. On the other hand, if C is equal to 0, or C is equal to infinity, or C does not exist, okay, so in either of these cases, that would be if one of these two terms pulled away quickly from the other one. So going to infinity means an grows much quicker than bn. Going to 0 means bn grows much quicker than an. And not existing means bad weirdness. In that case, then the test is inconclusive, which means we learn nothing from the limit comparison test. A very common error in interpreting the limit comparison test is assuming that if you get one of these results, that means that the two series have opposite behavior. That is not necessarily the case. It means we just learn nothing. So we only get a result from this test if C is positive and finite. And that conclusion is that both an and bn have the same behavior, and presumably you know something already about bn, so you can commute that conclusion over to the series you're interested in, an. So let's go back to the series that motivated this test and apply it to that series. All right, so this is the one we were working with earlier, and we couldn't quite get a direct comparison to work. So no problem, we'll use limit comparison. So again, as it's algebraic, we can make the comparison with leading term from the numerator, leading term from the denominator, so 1 over n squared. So that's a p series, it's going to converge, so we already know about the conclusion of this. So we know this is now a convergent series. We just have to prove it. Okay. Now, I want to really convey something essential here. If you have a purely algebraic series, you can always use the limit comparison test to compare it to a specific p-series. And in fact, you should just do that. Okay? Algebraic is French for use the limit comparison test. A little known fact. So we'll do that. Okay, so what do we have to do? Well, take this limit. So now, an over bn. We're going to take this limit so often that rather than stacking the fractions, let's write it as an times the reciprocal of bn, so n squared over 1. And this is going to, of course, approach, in this case, 1, because this is a purely algebraic limit, and we know by comparing the degrees, we just have to write leading coefficient divided by leading coefficient, so 1 over 1 in this case. All right, now, what is it about 1 from which we can draw our conclusion? Now, this is important, right? We must justify everything. 1 is positive and finite. The most concise way of saying that is just writing this. 1 is greater than 0 and less than infinity. What is our conclusion? Our conclusion is that the two series have the same behavior. Incidentally, you never need to designate what your an and what your bn are. It's always going to be clear that an is the series that you're investigating and bn is the series you're comparing to. So you never need to label them specifically as such. So the series AN and the series BN have the same behavior. Okay, good. Well, what does that mean? Well, we know that the series BN converges. And why is that? It's a p-series. 2 is greater than 1. So this is convergent. And our conclusion is that AN series is also convergent. And there we are. That's our proof. Okay, what about this particular series? So this one is not purely algebraic, because it's not polynomial over polynomial, plus or minus some radicals. This sort of looks like a geometric series, doesn't it? Now, it's not a geometric series because of this -1, but it's pretty close to a geometric series, and we would sort of expect it to behave like this thing, because way down the line with large values of n, there'd really be no difference between, this series and that series. Now, as a geometric series, we understand the behavior of this series. We could extract its r value, which is, in this case, 1/2. And since the absolute value of r, which is 1/2, is less than 1, we can conclude that this is a convergent series. So if we were to use a direct comparison, we would be needing to find a way to show that this is less than this. And that's not true, unfortunately. The thing on the left is slightly larger than the thing on the right. So we'll just have to use limit comparison test. All right, so to use the limit comparison test, we're going to let C be the limit as n approaches infinity of AN over BN. So AN is this guy, and again, we'll multiply by the reciprocal of BN, so that'll just be 2 to the n over 1. And this limit does approach the form infinity over infinity. And this is also not an algebraic limit, so we can't just compare degrees. They don't even have degrees, right? They're both exponentials. So one thing you could do is use L'Hopital's rule, but first you would have to set up, like an auxiliary differentiable function. So you'd let f of x be 2 to the x over 2 to the x minus 1, and then you would evaluate the limit as x approaches infinity of f of x, and full reign here to use L'Hopital's rule, you would get a conclusion. This limit actually approaches 1, and then you could just argue that the original limit approaches 1. We don't have to go that far. If we just put our Math 3a hats on, we can actually evaluate this one by dividing everything by 2 to the n. So we would get 1 over 1 minus 1 over 2 to the n. This was arrived at by, like I said, dividing everything by 2 to the n. And now we can easily see this limit approaches 1. All right. Now, what is it about 1 from which we can draw a conclusion? Okay. 1 is finite and positive. It's between 0 and infinity, strictly. So therefore, these two series have the same behavior. That's all the limit comparison test says. It never establishes convergence or divergence on its own. All it does is it says, yep, these two series behave the same way. Or, in the case where the test fails, it says, I don't know if they behave the same way. So that's all. Those are the only two options. So now we say, okay, well, we know something about Bn. That's this thing. This guy is convergent. Let's quickly justify. It's a geometric series. The absolute value of r is 1/2, which is strictly less than 1. Done. Therefore, this series, the one we are interested in, is also convergent. And there we are. You may have noticed that we are not working out any sums of series. And we haven't done that in a while, not since section 11.2. And yeah, that's because sums of series are generally very, very difficult to find. It's a completely different process that we would use, and we also don't really need them that often. So even though this series behaves very similarly to a geometric series, as we just established, and it converges, what its sum is, we don't know. So the a over 1 minus r formula, completely irrelevant, because this is not itself a geometric series. All right, let's investigate this particular series. And at the same time, let's be grateful that we're not confined to using the integral test, because no. So, all right, this is a purely algebraic series, right? Remember, purely algebraic is French for use the limit comparison test. In fact, it's pronounced purely algebraique. So great, we just need to find the p-series that this thing behaves like. Okay, well, let's just take the leading term from the numerator, so that's n. Leading term from the denominator, 3n cubed under a radical. So, okay, let's clean that up to see what p-series this really is like. So that would be n over, we don't even need that 3, right? So this is like n to the 3 halves. So, and this is n to the 1. So n to the 1 over n to the 3 halves. Well, that would be 1 over n to the 1 half. So there's our p-series that we're going to compare that to. We'll use the limit comparison test with the series 1 over n to the 1 half. Okay, well, this p-series here we know is going to be divergent because it's a p-series and 1 half is less than or equal to 1. So yeah, this is a divergent p-series. So we project that the original series will also be divergent. So let's first work out the limit. It's an over bn. So an is this monster here. And dividing by bn is like multiplying by the reciprocal, so we'll have n to the 1 half over 1. Okay, so this is like n to the 3 halves minus 5n to the 1 half over this thing. And this is a purely algebraic limit, so we just need to compare the degrees, right? But if we chose our bn correctly, then these degrees ought to match, right? If they didn't match, we would just get 0 or infinity as our limit, and those are the inconclusive cases. So what a waste of time that would have been. So that's the whole reason we so carefully select what we're comparing to, because yeah, these degrees are going to match. Numerator has a degree of 3 halves. The denominator has a degree of 3 halves. So this is going to be leading coefficient from above divided by leading coefficient from below. So 1 over rad 3. Okay, so what is it about 1 over rad 3 from which we can draw a conclusion? It's positive and not infinity. So therefore, these two series have the same behavior. Okay, we haven't yet asserted that Bn is a divergent series, so let's do that right now. And we'll justify that claim. P is 1 half, it's a P series. What is it about 1 half? 1 half is less than or equal to 1. That's why we know this is a divergent series. Okay, well, they have the same behavior, and the P series is divergent, so that means that the ugly series here is divergent. And we are done. Okay, so a question that frequently arises around this point in the lecture is, with the limit comparison test being so versatile, is there any point to the direct comparison test, right? The first test that we learned today, since with the direct comparison test, you have this added burden of making sure you get the direction of the comparison right Whereas with the limit comparison test, you don't have that problem at all. You just kind of can brute force it by taking a limit. And that's certainly true for purely algebraic, right? There's really no need to use a direct comparison on a purely algebraic when you can use limit comparison as we have been for those. However, a direct comparison test still has a place. You can use it to cleverly drop a term that's kind of distracting or making the problem difficult to work with. For instance, in this particular example, we have this pretty obnoxious looking cosine here. But with a direct comparison, we can throw away the cosine immediately. So we actually are going to use a direct comparison here. We're going to use the fact that sine and cosine lie between -1 and 1. All right, this is true. That's their range, right? Sine and cosine have this range. So this is particularly helpful in the universe of series because, well, we don't actually need this end of things. We can see that cosine of n is less than or equal to 1. And so if we add to both sides, we can see that 1 plus cosine of n is less than or equal to 2. And that means if we divide both sides by e to the n, we get 1 plus cosine of n over e to the n is less than or equal to 2 over e to the n. So we have the step here of our direct comparison. We are comparing the terms of the series we're interested in with the terms of some other series, the series 2 over e to the n. And 2 over e to the n is a convergent geometric series. And we can actually assert this. 2 over e to the n is convergent. We do need to justify, but for geometric series and p series, it's a one-liner, right? So this is geometric. The absolute value of r is 1 over e, not 2 over e. The 2 can be factored right out of the whole thing. It's just whatever's being raised to the n, which is 1 over e, and that's strictly less than 1. So the series is convergent. And we can conclude that the series we're interested in is convergent. All right. If instead you had chosen to do a limit comparison test, you would have had to deal with this obnoxious cosine in your limit, which is not easy. Probably would have needed the squeeze theorem to get the result you need. So no, direct comparison test is very helpful here. It will also be very helpful in the next example. All right. What about this particular series with a factorial? So we're going to have a way of handling series with factorials in a couple of sections that's really awesome, and it's my favorite test. It's called the ratio test. But we can actually knock this particular one out with a direct comparison. And that is, again, by taking advantage of a sort of hierarchy of growth rates that we're aware of. So let's note that n factorial is greater than or equal to 2 to the n. Okay, now this is not true right away because, for instance, 2 factorial is 2, but 2 squared is 4. So this would be the wrong direction of comparison for that. And also 3 factorial is 6, 3 times 2 times 1, and 2 raised to the 3 is 8. So again, it's not true for 3. But starting with 4, this is true. And then it's true forever after that. So 4 factorial is 4 times 3 times 2 times 1, which is 24, and 2 to the 4 is 16. And indeed, 24 is greater than or equal to 16. So if you're ever stuck with a stubborn factorial and you need to use some sort of comparison, you can always show that it's eventually the factorial will be bigger than 2 to the n. In fact, it'll eventually be bigger than anything to the n. So 5 to the n or 12 to the n. It might take a long time before that starts happening, but it will take over. Factorial grows much faster than exponential growth. So, given that, we can use direct comparison because we can see that 1 over n factorial will be less than or equal to 1 over 2 to the n. Right? Just by taking reciprocals, you would flip the direction of the comparison. All right. So, what do we know about this series? Well, it's convergent. It's geometric. because r is equal to 1 over 2, and 1 over 2 is strictly less than 1. So we can conclude that 1 over n factorial is convergent. So we didn't have to compare it to 1 over 2 to the n. Like I said, we could have compared it to 1 over 3 to the n, or 1 over 4 to the n, or whatever. But you could also compare this with a p-series, because the hierarchy continues. We have factorials growing faster than exponentials, which grow faster than any power of n, so like n cubed or n to the fourth or n to the fifth or whatever, of course, which grow faster than ln of n, the natural logs, which grow faster than constants. So there is sort of a hierarchy in the background here that these inequalities are eventually true for any particular pair that you pull out of that. So it's safe to make those comparisons. This means that we could have compared to, say, 1 over n squared, and because 1 over n squared is the term of a convergent p-series, we would have drawn the same conclusion, of course, that the original series is convergent.